Here we are at the squeeze theorem from our 1.3 number 2 set of notes. Now here is again the formal definition for the squeeze theorem, but let's go ahead and just look at the graph and see what that is representing and showing us. As you guys can see, we have g of x in between this function f of x and h of x throughout the entire time. In other words, g of x is not kind of like above 1 or below f of x. It doesn't really kind of deviate from that. So as a result, if there's a case then where f of x and h of x, if they have the exact same limit, in other words, the limit as x approaches, in this case, this particular a value, notice they end up, the left sides meeting up at the same exact spot for h of x and f of x. If in fact g of x is in between these two functions, then by force of h of x and f of x, it has to become the same exact limit. Alright? That's pretty much what the squeeze theorem is saying. It is literally squeezing this function into that same exact limit. That's why it's called the squeeze theorem. Now, just looking at example 3 and kind of knowing the squeeze theorem, we see that we have the limit as x approaches 0 of this particular function. Now, because these two functions are being multiplied together, let's go ahead and apply our limit, our product property, and apply that limit to both items. So when we do that, we end up then with the limit as x approaches 0 of x squared times the limit as x approaches 0 of our cosine of 1 over x. Now, the limit as x approaches 0 of just x squared, that's a nice, easy one that just comes out to be 0. So we're not too worried about that first guy. The issue starts to come into the second piece. So we're multiplying that by this limit. When we go ahead and try doing direct evaluation, we end up with the cosine of 1 over 0. And we can right away see that this inner piece is an undefined statement, thus making then the cosine of an undefined statement not even possible. So we have 0 times something that is undefined. Now what we're going to go ahead and do is use our squeeze theorem that we just learned about and prove what this true limit actually comes out to be. Alright, so before we even start with anything, let's go ahead and just graph what this function looks like and see maybe what value is it approaching. So all I've done is gone ahead and gone to y equals, and then we're going to enter in our function. It's x squared times the cosine of 1 divided by x. Hitting graph. We end up with the following function. Well, it looks to be about 0. It looks to be about 0. Even if we go ahead and hit second table, we see that this is a very, very, very small number, really close to 0. And I would imagine on the other side it would be as well. So let's go ahead and hit second quit, kind of getting out of that table. Going back to our notes. We are thinking, so we think our limit is going to be equal to 0. It looks like it's going to be 0. Alright. Now some instructions tell us, okay, let's use the calculator and see what does just that cosine of 1 over x look like. Now again, this was the function that was giving us the issue. The x squared was just fine, so we didn't have to worry about him. So let's go ahead and see maybe what's going on with just this guy. So, going into our function, let's go ahead and delete that x and squared and hitting graph. Now in just looking at our graph, we can see that it looks like we are a little bit more than 1, or I'm sorry, a little bit more than negative 1, at least our y values are a little bit more than negative 1, but a little less than positive 1. Maybe if we even zoom in to kind of illustrate this point. there you can see, hopefully a little bit better, that we are a little bit, our y values are a little bit more than -1 and a little bit less than +1 throughout the entire throughout the entire time. And we notice that we have some craziness that looks like it's happening around 0. So it kind of looks like it's just oscillating back and forth with one another. Maybe if we zoom in some more, let's see what happens. Yeah, so it's really kind of just going back and forth, back and forth, back and forth, and really kind of crazy, especially around that x value of 0. So let's go ahead now and graph. Let's maybe graph our standard one, but a little bit zoomed in. So we're going to go to zoom 6. And I think it was the second zoom that we tried. So maybe the second zoom. Yeah, let's go ahead and graph what this one is on our first graph. So again, this guy is y is equal to the cosine of 1 over x. So around 1, and we were under 1 at least, and we were above -1. Well, we saw it kind of plateau at 1, so the side should be around 1. And then it kind of dipped down and kind of came back up. And we kind of saw this just like kind of crazy oscillation going on. And there was a lot of things that were going around 0. Now if you zoom in quite a bit more, you would see that it's just kind of like becomes a block because it's just oscillating so much around 0. All right? But I didn't want to burn too much time just kind of working on the zooms. So more or less, here is our graph. All right. Now let's go ahead and go back to our original function. Let's see what that looks like. So going to our graphing calculator, hitting y equals, we're going to hit second, insert. So that way we don't have to retype the whole function, x, and then squared. Now going ahead and hitting graph, we see what almost appears to be like a mustache or a bat kind of just flying. But it's hard to really see maybe what's going on close to 0. I mean, it looks like our limit's going to be 0, but it looks almost like there's a little bit of a gap going on here too. So maybe let's go ahead and change up our window a little bit. So I'm going to change my window, my minimum x value. Let's change that to -0.3. I'm going to change my maximum to +0.3. My scale, we'll go with 0.1. My y values, I'm going to get really, really small. So we're going to go to like -0.03. And our y maximum will go to +0.03. Oops. Let's get rid of that. There we go. And our y scale, let's go by point. Oh, we'll just say 0.01. All right. Now let's go ahead and graph and see what this looks like. Essentially what we're doing is because of our decimals, and you guys can kind of see that we're tenths or hundredths, we're zooming in a great deal just to see what's going on closer and closer to 0. So let's look at our graph now. So we see something that at least looks symmetric on the left side and the right side. So that's kind of a good sign. And it looks to be like it's 0, but again, it looks like it's oscillating back and forth quite a bit there. All right, so let's go ahead now and actually draw this for our second graph. So we should have something that looks like do a little bit of a resketch on the right side. Alright, so more or less, that is our image that we are seeing when we combine the two functions together. So again, this was our y is equal to x squared times the cosine of 1 over x. So it really looks, again, this is what we think, that the limit is equal to 0. It really looks like it is, in fact, 0. Now, let's just for a moment go ahead and graph x squared and negative x squared. I'm going to go ahead and go to y equals. I'm just going to graph these as two totally different functions. Okay? So we have x squared and negative x squared. Going ahead and hitting graph. And so more or less, this is the image that we are in fact seeing when we went ahead and graphed negative x squared and that positive x squared. Okay? And we can see very, very clearly that our x squared times cosine of 1 over x is constantly between these two functions. So now let's go ahead and talk about our proof. Our goal is to go ahead and prove that the limit as x approaches 0 of x squared times the cosine of 1 over x is in fact what we think it to be, 0. And what we're going to do is we're going to use the squeeze theorem to actually prove that this is in fact true. Now, if you recall, the squeeze theorem pretty much just said that if we had f of x, and as long as that was less than or equal to some g of x function, which is less than or equal to some h of x function, for all x that are not equal to 0, we need two functions, f of x and h of x, such that g of x is always going to be in between them for any x that's not equal to 0, and the limit as x approaches 0, so the limit as x approaches 0, not the actual value where x is 0, of f of x is equal to the limit as x approaches 0 of h of x, which is also equal to 0. Because again, we're trying to prove that because g of x is between these two functions, their limits are also exactly the same, 0, which again is what we are hoping that it also matches. Because it looks like from our graph that it is in fact 0. Now if you recall, our original function, just the cosine of 1 over x, was always in between -1 and +1. Right? We can even look back at this graph. This was just the cosine of 1 over x. It was constantly between -1 and +1. Never deviated or went outside that. Now keep in mind, our function though was x squared times cosine of 1 over x. So we need our true function, x squared cosine of 1 over x, still in the middle. Because again, that's what we're trying to prove. Well, in order to get that x squared there, we'd have to multiply everything by that x squared. We'd have to multiply all terms by x squared. So over here then, -1 times x squared just gives us negative x squared. Over on the right side, 1 times x squared just gives us x squared. Now let's go ahead and just look at the individual limits of this guy, negative x squared, and the limit as x approaches 0 of just x squared as well. So we have the limit as x approaches 0 of negative x squared. Well, if you go ahead and use direct evaluation, that just comes out to be 0. Likewise, the limit as x approaches 0 of x squared, well, again, using direct evaluation, you just plug that in, also comes out to be 0. So, because they actually end up coming out to be the same limits, notice too, this guy in the middle is always in between these two functions. We can actually even look at the graph and verify that. Here's positive x squared, here's our negative x squared. Our x squared cosine of 1 over x is always in between there. It's never going to go outside of them. Then as a result, the limit as we approach 0 from both functions is going to squeeze that x squared cosine of 1 over x, such then that it has to be 0. So then by the squeeze theorem, the limit as x approaches 0 of x squared cosine of 1 over x must be 0. All right. So again, that is the squeeze theorem example 3. I know that proof was kind of, maybe a little hard to conceptually see. If you have to take a few times to look it over, please do. And obviously, if you have questions, I think that this is a little bit of a harder thing to kind of grasp, the squeeze theorem, especially with the example. So if you have any questions, again, please feel free to ask me. All right. So again, though, that is the squeeze theorem, example 3, and the proof behind why it works.